I welcome you all for this session of artificial intelligence in the petroleum industry. Um, Today's topic is about emerging AI techniques for enhancing exploration and production success. So this is a kind of AI technique that we are going to use to enhance the exploration activities and production activities. And the technique that we are going to adopt is support vector machines SVM. So this is an AI technique that we are going to discuss about the algorithm related to that and how it is going to impact the exploration process and production process that we are going to see. So let us dive into that. So first of all, we are going to introduce what exactly is this technique, support vector machines. We will discuss the use of support vector machines for reservoir modeling and characterization. SVMs are a type of machine learning algorithm that can be used to learn complex relationships between data points and outputs. In the context of reservoir modeling, SVMs can be used to predict reservoir properties such as porosity, permeability from seismic data or other well logs. So this technique is going to be used to estimate reservoir properties like porosity and permeability. So it is a kind of model to reduce the complexity of different dimensions. Like if you have more dimensional data is there, then defining that property will be difficult. So if you reduce that dimensions, imagine you have three-dimensional axis, then if you start estimating properties in 3D, it could be difficult. So that you have to reduce 3D to 2D. In that way, we have to so it will become more easier, like xy could be easier than xyz. So in that way it will be helping you. More dimensionalities in reservoir, heterogeneity will be more, complexity will be more. So SVM, what exactly it will do is it will reduce that dimensions, number of dimensions can be reduced, and finally it will try to generate a hyperplane. So in place of traditional xy axis, it will create its own axis so that uh, with the reduced dimensions, from that we can able to estimate unknown values or nearby values. We can form a relationship between them. What is reservoir? Reservoirs are underground formations that store oil and gas. So this is a basic definition of reservoir engineering, where the crude oil have been deposited below. So reservoir modeling is the process of creating a computer model of a reservoir. Generally, we can't able to assess how a reservoir looks to be. So only the way we can able to do it is by modeling it. It is a kind of model, a simulated model with the dimensional properties. If you have more data based on that, we can construct a model in the software. So that can be analyzed for dimensionality. Reservoir characterization is the process of determining the properties of reservoir, such as porosity, permeability, and so on. For petroleum engineering, it is these are the important characteristics that has to be assessed. These are complex, and every location the properties will be changing. So you are supposed to estimate all these properties all together as much as possible. If you could get the data that much accurately, you can able to forecast the predictions. Reservoirs are important for the production of oil, gas, and water. Reservoir modeling and characterization are essential for the development of and management of these resources. So when it comes to SVMs, are the type of machine learning algorithm that can be used to learn complex relationships between data inputs and outputs. So as you can see, it will try to create a relationship between input and output. SVMs can be used for classification and regression tasks. And we have number of classifications in reservoir. So reservoir classifications, different types of reservoir, there also it will be helpful. And regression tasks. So we are going to already discussed about linear regression and linear uh, way of solving the problem and the logistic way of solving the problem. So these regressions, wherever it is there, SVM can be applicable. SVMs are well suited for tasks with high dimensional data and limited data. As I said earlier, so more dimensions, complexity will increase. So today this technology is available in artificial intelligence to reduce that dimensions, and we can increase the output efficiency by reducing these dimensions. Wherever limited data is there, so machine will be learning with this limited data, and based on that it will start to create a hyperplane to reduce the complexity. SVMs are a powerful machine learning algorithm that can be used for a variety of tasks. SVMs are well suited for tasks with high dimensional data such as reservoir modeling, where there may be many different input features. As I said, reservoir modeling requires more. Why? Because you are going to create a simulated model of a rock. For that, you require huge amount of data. All this data will be integrated. It will be analyzed, and based on that, you are going to see an outcome. So through that, we will be understanding how a reservoir looks to be, how the saturations will start to move from one direction to another direction, and the kind of porosity and interconnected pore spaces. All these things can be analyzed if you have good amount of data. SVM are also well suited for tasks with limited data, as they are able to learn from a small number of training examples. Artificial intelligence is always about, first of all, where it will be trained through machine learning. Then it will start analyzing the outcomes by the inputs what you are going to give. So first of all, it has to learn from the available data, and with that itself, it is going to provide you the insights. So how you are going to get the insights? It has to be learned. With limited data is there, fine. If you have limited data, you can upscale to a larger data with the help of AI. And SVM will help you to reduce the complexities of dimensionality, so that it will be easier for us to understand, whenever the data is being generated in a linear way. SVM machines for petroleum industry. We will explore SVM and their applications in the field of petroleum engineering. SVMs are powerful supervised machine learning technique. Supervised means you already know what is the outcome that you are expected. If you don't know it, then we say it as unsupervised. So you know what the result you are going to you are expecting from the input. So that outcome, accurate outcome, that if you could able to regress that kind of analysis, that we will be saying it as supervised learning. So SVM is also a supervised learning. Means you are going to give limited data, and you are asking it to provide an insight of expected outcome. So it is going to create a hyperplane where the other parameters will relate to each other with the help of this hyperplane. So that is what we are going to see how it will be constructed in algorithm. So in petroleum engineering, SVMs are finding increasing use due to the ability to handle complex and a non-linear relationship with the data sets. Generally, the data we have to find relationship. Unfortunately, a lot of data will not have any sort of linear relationship. So right now, with the help of SVM, we are going to create relationship between, you know, uh, available data that we have, and we will reduce the dimensionality with that. So this is a small glimpse of SVM. What does it do? You can see on the right side there is an image separating some colored balls. Pink color is there, green color is there. So it was separated by a layer. Like if you could observe over here, so this was separated by a layer from different balls. So here also proportion is there, here also equal proportion is there. But how we know that these balls belong to one category and these balls belong to another category? So this is what SVM algorithm will do. So this can be considered as pressure points in reservoir. So we are going to cluster these pressure points separately and this one separately. So it will be separated by a layer. So yeah, this is what exactly I am contexting it as hyperplane. So hyperplane will separate the data into different categories. Okay, so generally if you see with the dimensionality, you cannot able to distinguish between these points, but with the help of hyperplane, you can separate that into different categories. That is what SVM will do. And more complex data, we are going to use it in petroleum engineering, and it is used for reservoir characterization, production optimization, and everywhere. So let us, these are the applications that up to now what we have discussed, and let us get into the algorithm. So just try to understand. So we have 1, 2, 3, 4, 5, 6 points. So 6 variable points that we have. X is an independent variable, Y is a dependent variable. So X axis, Y axis. So Y is dependent on X. So we have 4, 1, 4 minus 1, 6, 0, 1, 0, 1, 0, 1, 0 minus 1. If you put it in XY coordinate, so these points looks to be like this: 1, 2, 3, 4, 5, 6. So in this axis, we have two axes. One is X, another one is Y. So these two axes represents as two dimensions. So we have kept these points on two dimensions. So what SVM will do is it will reduce to one dimension. So this is what exactly is the objective of SVM. So the points were less and complexity is very much less for this example. But when in real time, you will be having number of dimensions. Based on that, you need to categorize these points. So you can take x-axis as porosity, y-axis as permeability. Like that, capillary pressure, you can include compressibility, formation volume factor, wettability. So you can have n number of variables in the reservoir. But let us talk about in a simpler term. We have two variables, one is x and y axis, and we kept all these points here. So here what we have to do based on these two dimensions, we are going to convert that into one dimension, and we need to separate out of these points which points belong to one category, another point belongs to another category. So let us say that certain points belong to positive category, the points which doesn't belong to positive category belongs to negative category. Let us think like that. So if you see, these points are little bit close together and these points are little bit close together. Let us try to take the points which are nearby each other. So the point 1, 0, 4, 1, 4, minus 1. So this looks to be, separated, these three separated and these three separated. We can think that you can separate these points by drawing somewhere hyperline in between somewhere, but we don't know where exactly we have to draw. But the points close to it we have to take. So we have 3 points: 1, 0, 4, 1, 4, minus 1. Sometimes we may have 2 points. So here we have 3 points. So let us take that 3 values as vectors: S1, 1, 0, that is this side, and 4, 1, 4, minus 1, S2 and S3. So these are support vectors which are close to each other, where we are planning to separate into different categories. So this is the first step. S1 is equal to 1, 0. That S1 is the support vector over here, 1, 0. S2 is 4, 1. S3 is 4, minus 1. So next step is to add 1 to each of the support vector. So you can see S1, S2, S3, 1, 0, 4, 1, 4, minus 1 as there. So below we have added one more bias term, minus 1, 1, 1. So one value support vector is having minus 1. Other two values belong to plus 1, plus 1. Why it is? Why? Because 4, 1, 4, minus 1 belong to positive category and 1, 0 belong to net. So what we are thinking, what is the plan we are having is, we are going to frame a hyperplane in between the closest points near to each other. So the one which is left side of that hyperplane, we are assuming that that will be negative, and right side of that hyperplane, we are assuming that it is positive. And based on that, we are giving minus 1 which belongs to negative and plus 1 on the other side which belongs to positive. So this is what we have assumed. So let us start working on this, and we convert these vectors into equations. So a1, a2, a3, these are three variables and that were given in this equation: s1, s1, s1 into s1, s1 vector into s1 vector, s1, s2. So first equation s1 is common, second equation s2 is common, third equation s3 is common. So in the same way in column, s1, 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 s2, 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 s3, s3, s3. So in first side, x-axis wise, S1 will be common, and column wise, S1 will be common. So like that we have to frame the equation. So if you keep the equation and keep the bias at the last, so this you have to cross multiply S1 into S1, S1 into S2. So let's see if you cross multiply how the equation will be. So the points S1 into S1, 1, 0, 1, 1, 0, 1. So one, this one into this one. So like that we are going to use for S1 into S2, S1 into S3. So like that we have kept all the equations. Then let us see, after putting this equation, 1 into 1, 0 into 0 plus 1 into 1. 1 into 4, 0 into 1 plus 1 into minus 1. Like that you have to put all the equations. So this is the internal form of these equations. If you expand it, then you will be getting the values of 2a1 plus 5a2. So this value, these values of 1 into 1 plus 0 into 0 plus 1 into 1, that will be 2a1. Like that 5 represents here and 5 represents here. Okay, so like that we have to estimate for each and everything. In the same way 5 represents here and 18 represents here, like that. So all together if you keep the values, so you will be getting three equations with three variables, a1, a2, a3. So you have three equations with three variables. If that is the case, you can solve this equation. Since you have three equations, after solving it, you will be getting a value of a1 as minus 2.5, a2 as 0.39, and a3 also you have 0.39. So this is what up to now we have done. First of all, what we have to do is we need to convert support vectors into equations. After converting support vector into equations, S1 into S1, S1 into S2, like that, you replace the values with all the vector forms, and after that you have to solve it. So 1 into 1, since it is vector, 1 into 1 plus 0 into 0 plus 1 into 1. 1 into 4 plus 0 into 1 into 1 plus 1 into minus 1. So like that we have to put every answer, every iteration. Then you will be getting the values as 2 into a1, 5 into a2, 5 into a3. Like that you will be getting it. And finally solving this three equations, you will be getting a1 as minus 2.5, a2 as 0.39, and a3 as 0.39. After this, you are going to use an equation, that is the overall weighted equation. W is equal to summation of I is equal to 1 to 2 ai into si. So all the a1, a2, a3 values were known. S1, S2, S3 values were already defined. So we are going to put these values over here, and with the vector values, and then you are going to get minus 2.5 into 1 plus 0.39 into 4 plus 0.39 into 4, you will be getting 0.62. Minus 2.5 into 0, that will be 0. 0.39 into 1 minus 0.39, that will be 0. And finally minus 2.5 into 1 plus 0.39 into 1 plus 0.39 into 1, you will be getting 3.3. So you can round off this equation. So 0.62 can be written as 1. If it is less than 0.5, you have to make it as 0.5 alone. So 3.3 can be written as 3. So this is what we have to do for round off. Then we have to construct the plane. So you got the values as 1, 0, 3. So what does this represent? 1 represents x-axis, 0 represents y-axis, 3 represents intercept. So when there is a x value is equal to 1, y value is equal to 0, that means the line will be parallel to x-axis. This is how we can able to understand. So first of all, we need to know if x is equal to 1, y is equal to 0 means the hyperplane is parallel to y-axis, and it will be it will be sent to a distance of intercept. So what is the distance that we have got? 3. So 1, 2, 3. This is 0, 1, 2, 3. So this is the point we have to locate, and x1, y0 means it is parallel to y-axis. Exactly, x is equal to 1. X is equal to y0 is parallel to y-axis. So if the case is like this, if x is equal to 0, y is equal to 1, then it will be opposite. It will be parallel to y-axis, then x. So that will be looking to be like this. So this value is where x is equal to 0, y is equal to 1. So that will be parallel to x-axis with an intercept of 1. So intercept means distance from x-axis to the hyperplane. So this is the hyperplane. Okay, so this is how it will be represented. So right now with the answer that with the variables that we have, we got hyperplane, which is exactly stood at 3 points away from 0 on x-axis and which is parallel to y-axis. So you can see these points are separated from these points from a hyperplane. So this is the hyperplane which exactly separates these 2 points. Right now, no need for x-axis or y-axis. So this alone is it can be used as an axis. So from here onwards, the distance will be measured for each point. So that will be equivalent to those points which were measured. So if you know the distance from this hyperplane to each points, then we can able to estimate some relation between them. So the points which are on the right side are positive, the points which are on the left side are negative. If you consider like that, this is the hyperplane that is subdividing all the points. So as I said, x is equal to 1, y is equal to 0, the intercept will be 3. In the same way, I will remove the things. In the same way, if x is equal to 1, so we will be having three case studies. One is x1, y0, that is like parallel to y-axis. x0, y1, that will be parallel to x-axis. If x is equal to 1, y is equal to 1, then it will touch x and y axis exactly with 45-degree inclination. So like a slant line, it will be separating. So the points will fall on this side and the opposite. So if x is equal to 1 and y is equal to 1. So right now I have written a graph where x is equal to y is equal to 1 and the intercept value is 1. So from x-axis it should be 1 and y-axis also it should be equivalent to 1. So this is how the case study will be subdivided into two different axes. So in conclusion, support vector machines offer a powerful and versatile approach for various tasks in petroleum engineering. Their ability to handle complex data and non-linear relationships makes them well suited for tasks like reservoir characterization, production optimization, and drilling optimization. By leveraging SVMs, petroleum engineers can make more informed decisions, leading to improved efficiency, reduced cost, and ultimately a more sustainable approach to oil and gas exploration and production. As research and development in machine learning continue, we can expect even further advancements in application of SVMs within the petroleum engineering industry. So this is about the topic for today, and let us meet in our next topic. Uh, Thank you for today.